Okay, let me just revise a definition we had for the polyhedral cone. The wording was correct, but it was a little bit ambiguous. But before that, let me just give you the set of problems that you want to work on. The second set, I did not put it on the board. I'm just putting it on the board because we want to capture it also on the camera. And the third set, I'm going to also put it down on the board. So problem set number 2, you should have this. This is from, again, Bazara, Jarvis, and Sharali, chapter 1, 25, 27, 29, 32, and 33. Does this agree with what you have from Hatice's notes? Did she assign? Nobody seems to answer. Has she assigned homeworks? Okay. This is supposed to be what it is. And the third set, that's number 2. The third set from the same book, chapter 2, 3, 4, 25, 29, 36. Incidentally, I also cover stuff that's not included in that book, so make sure that you've got that in your notes. Today's stuff will be mostly different from what's available in the book, okay, in chapter 2. Also, the previous material on requirement space, that was that's covered in Bazara, Jarvis, and Sharali, so you can take a look at that. But Fourier-Motzkin elimination is not covered in the book, so but you've got the main understanding, so you shouldn't have any problem with that. So let me just revise the definition of a convex cone. Was it the convex cone that we were talking about?
Polyhedral.
Polyhedral cone, okay. Okay. If all defining hyperplanes of a polyhedral set pass through the origin, then such a polyhedral set is called a polyhedral cone. And if the polyhedral set has a constraint of the form, well, a polyhedral set is the intersection of either hyperplanes or half spaces. For a hyperplane, the defining hyperplane is just the hyperplane itself, okay? For a half space, the defining hyperplane for that half space is the equality version of the definition of the half space, okay? So, if your half space is, if you have a hyperplane, then the defining hyperplane is itself. If you have a half space of the less than or equal to form, then the defining hyperplane is simply the same set with equality. A transpose X equal to alpha. And similarly, if H is greater or equal type with normal A, then the defining hyperplane is the equality version of that. Okay? If anybody is not following, I'm going to write it down explicitly, but we're just losing too much time writing down everything explicitly. Okay? So anyway, that's what it is. Let's just continue with convex hulls. So suppose you've got points x1, x2, up to xk in n-dimensional space. If you take convex combinations of all these points, and the set of all such convex combinations is your convex hull. So the set of all convex combinations of the points x1 through xk is called the convex hull of these points. So in taking the convex combinations, you take a number alpha lambda 1, multiply it with the first vector. You take a number lambda 2, multiply it with the second vector, so on and so forth. So each vector is multiplied by a scalar lambda j, the jth one, and that forms a convex combination if you require each lambda to be a number between 0 and 1. Together with the fact that they add up to 1. Okay, so these last two conditions ensure that you have a convex combination. Okay? And the set of all such points is your convex hull. So the feasible set of this linear system of inequalities. Where are the inequalities? So we're talking about a point U obtained by this, using these. And so the set of U obtained as a feasible solution to the above system constitutes your convex hull of these points, or gives the convex hull of these points. Okay? All right. So just pictorially, in 2 dimensions, if your points are, for example, these points, x1, x2, x3, x4, x5, x6. These are points in your 2-dimensional set. So this is an example for n equals 2. You take all possible convex combinations and you start generating all these points that are contained in this shaded region. That's your convex hull. course, convex hulls are convex sets. You can prove that because they are actually formed by taking convex combinations. Suppose you have a convex set S in the n-dimensional space, then extreme points of such a set may or may not exist. But if it exists, it fulfills a certain condition. So let's just write it down. A point X in S is an extreme point of S if X cannot be expressed as a strict convex combination of two distinct points of S. Now, I don't remember if I defined the wording strict convex combination before or not. Did I do that or not? We did define convex combination, but strict convex combination means if in the convex combination, if you take the multiplier lambda as a number strictly between 0 and 1, different from both endpoints, then in that case you have a strict convex combination. Okay? So this requires your lambda to be different from 0 as well as 1. But it's a number between 0 and 1. Okay. So this definition simply says the following. X is an extreme point of S if there do not exist distinct points. Distinct means they are different from each other. Distinct points U and V in S and a real lambda in the open interval 0 to 1 such that X is lambda times U plus 1 minus lambda times V. Okay? So you're defining something here. You're defining an extreme point here by the non-existence of these conditions. Okay? All right. Equivalently, well, I'm giving you these equivalent versions of the definition because sometimes to be able to prove something, one angle or one way of defining something may be quite useful, whereas the other one may not be that much handy for that particular context. Equivalently, X in S is an extreme point of S if U and V in S and lambda in the open interval 0, 1, well, not and, but just comma, UV in S, lambda in 0, 1, and X equals lambda U plus 1 minus lambda V. This whole statement implies U equals V. They cannot be distinct. Okay? So if you pick 2 points, not necessarily distinct here, and if you pick a lambda, and if you are able to write X as a convex combination, strict convex combination of those 2 points, then it should be the case that U equals actually V. In which case, of course, the implication is they also equal X. Okay? Because that's what you get when U equals V. Okay. So extreme points are important in optimization as well as in linear programming. For example, if your feasible, if the set under consideration is this set, suppose that's your S, it's the unit disk situated at the origin, with center at the origin. Now this set has infinitely many extreme points. Each point on the boundary is an extreme point. Each point on the boundary. All right, the definition of S in this case is it's the set of points X such that the norm is less than or equal to 1, assuming that the radius of the disk is 1. Okay? Now, what about this set? In this case, your S is defined essentially the same way, except that the norm is strictly less than 1 rather than 1. So the boundary points are not included. Those points with radius being 1 are not included, whereas anything less than 1 is included. In this case, there's no extreme point. Because regardless of which point you pick in the set, you will be able to form a little neighborhood around that point with small enough radius, and you will be able to pick 2 points in the ball or in the neighborhood around that point, and you will be able to express X as a strict convex combination of those 2 points. Does everybody see that? If you don't, raise your hand, okay? So it doesn't matter how close you are to the boundary. There's always a strict positive number which defines a little neighborhood or a ball around that point where the strict convex combination can be actually worked out. Okay? All right. What about this set? Suppose you have a polyhedral set such as this one. So S is the inside as well as the boundary. In this case, these points are all extreme points. And there's no other extreme point. Okay? You can see that I cannot really express this as a convex combination, strict convex combination of any other 2 points, whereas a point such as this one can surely be expressed as a strict convex combination of some 2 other points. Non-extreme point, whereas these corner points are extreme points. And it turns out, of course, that in linear programming, when you try to minimize or maximize an objective function, if there's an optimum solution, it turns out that some extreme point will qualify as an optimum solution. Okay? That's one of the fundamental theorems which we will get to. Vertex of a polyhedral set. So let's assume you have a polyhedral set P in the n-dimensional space. A point x bar and the polyhedral set is a vertex of the set under consideration if there exists a vector C in n dimension such that C transpose x bar for the particular point of interest is strictly less than C transpose y for every y in the polyhedron except x bar. Now, this definition is not in Bazara-Jarvis-Sherali, so let me just illustrate what it is trying to do. Suppose you've got some kind of a polyhedral set, such as this one, for example. So P is this set. And suppose x bar is this point. In this case, x bar is a vertex. Why? Because there's a C vector such that when you take the dot product of C with x bar, you obtain a certain number, say B, whatever it is. Okay? And when you look at this definition, this is by assumption some number B. And for every point other than x bar, C transpose y is less than, greater than B. So this consists of points of the form y such that C transpose y is strictly less than B. Okay, this part. Of course, with y being different from x bar, because for y equals x bar, of course, you've got equality. Okay. Over here, on this side, you've got points. Well, we're not really interested in that, because P is not there. Okay, the polyhedron is not there. But this is basically what it is. For x bar, you've got equality. For any other point inside the set other than x bar, you've got strict inequality of this form. So that's a vertex. Sorry, I wrote it the other way around. Yeah, it should be this way. Yes, thanks. Because that's how we have it here. Okay. In this case, which way does C point? It's perpendicular to this. It's the normal of that. Which way does it point? Since you're growing larger here, it's pointing this way, right? That's your C. Okay? You get larger when you move along the direction of C. Okay? Equivalently, x bar is a vertex of the polyhedron P if and only if there exists a vector C in Rn such that P is a subset of the set of points Y where C transpose Y is greater than or equal C transpose X bar, and that P with X bar removed is a subset of the set of points Y such that C transpose Y is strictly greater than C transpose X bar. So, the first set includes all points including X bar that satisfy this inequality. The second set excludes X bar, and so you require strict inequality. So these are equivalent. Okay. This is a side result. Let me just give it to you. Let P be a non-empty polyhedron. And X bar be a point of P. Then the point X bar is an extreme point if and only if it's a vertex. So, as a result of this theorem, actually, extreme points and vertices, they are the same, they are different names for the same object, okay? For the same geometrical object. All right, I'll give you only one way of the implications. The other way, you can work it out at home, okay? So let's just prove that being a vertex implies being an extreme point. So we suppose X bar is a vertex of the polyhedron. And when that is the case, of course, there's a C, then there exists a vector C in Rn such that the definition applies, which means C transpose X bar is less than C transpose X for every X in P minus X bar. Okay? So, I pick 2 points U and V in P minus X bar. Well, let me do it this way. P with X bar removed, with U and V being distinct. And I pick a number, lambda, in the unit interval 0, 1, except it's in the open interval 0, 1. Okay? So what am I trying to prove? To be an extreme point, well, by assumption x bar is a vertex, we're trying to prove that x bar is an extreme point now. So I shouldn't be able to prove that x bar is or can be expressible as a strict convex combination of two distinct points. That's what we are getting at. Okay? So that's why I picked my u and v arbitrarily, except that I made sure they are not the same. And I picked my lambda strictly between 0 and 1. Now, when you look at C transpose U, by assumption, U is in P minus X bar, so you've got this. Okay? And the same holds true for the other one, V. So that one is also greater than C transpose X bar. Okay? So when you form the convex combination, which is C transpose lambda U plus 1 minus lambda V. When you look at this, this is necessarily greater than C transpose X bar. Why is that true? Because when you open this up, of course, you get lambda C transpose U plus 1 minus lambda C transpose V. We know that this part is greater than C transpose X. This part is also greater than C transpose X bar. So when you replace both of them with C transpose X bar, you get lambda times C transpose X bar plus 1 minus lambda C transpose X bar, which gives you C transpose X bar. Okay? So these two conditions certainly imply, together with the fact that lambda is a positive number, okay, between 0 and 1. So that X bar is different from the convex combination lambda U 1 minus lambda V. Because if they were equal, you should have equality here rather than strict inequality. Okay? Different. So X bar is different from that. Make sure that you understand the first proof and then work on the second proof, the second implication, and that will do the job. Okay? Questions? I'm sure in linear algebra you must have talked about subspaces to some extent. Have you heard the term? Let me just raise, let me see your hands. 4 years ago. In my course or in some other course? 4 years ago in the linear algebra course or in 202? Well, you don't remember though. How about the double E? Huh? You've heard of them. Okay. This is a definition again. A subset S of the n-dimensional space is called a subspace. If the linear combination of any 2 points of the set is also in the set. That's it. Okay? If xy in S and alpha beta being real numbers imply the linear combination alpha x plus beta y is also in S. Maybe I'll give you a few examples of this. This is really a straightforward definition, but there's one thing to remark here. The origin is always in S. Why is that true? So, because regardless of which points x and y you pick in S, you can always choose alpha and beta to be 0, in which case you get 0, and it should be in S. Okay? So, that's the way things are, and that's an important requirement. Okay? Let me see if I have any example here. As an example, if you define, for example, S to be the set of points in Rn such that A transpose X is less than or equal to B, this is a half space. Okay? The question is S a subspace? The answer depends. Okay? Depends if the conditions are fulfilled or not. Generally speaking, if your subspace in 2 dimensions, sorry, not subspace, but if your set S is this way, where the origin is here, what do you think? Is this a subspace or not? Why?
You can take 2 vectors there and on the x and y axis maybe, and you can form a linear combination which is above.
Okay. Which is
above the line.
Over here somewhere. I see. Okay. You can pick this to be x, pick that to be y, for example, and you take just some positive alpha and positive beta, and then so alpha x becomes this one, right? When you multiply it with positive alpha, the other one becomes this one, for example, beta y, and then when you take the sum of them, you get this point. That's your alpha x plus beta y. And so this point is not in S. For this reason, this is not a subspace. Good. Another example. Suppose S is that hyperplane passing through the origin. Is that a subspace or not? This is defined by A transpose X equals B for some A and B. It is a subspace. So this one is not a subspace, but this one is a subspace. Because if you pick any 2 points on the subspace or on the hyperplane, multiply them with any scalars, take the linear combination, you will definitely have equality again, because x, y in S, alpha, beta, real imply that alpha x plus beta y times A transpose times this, okay, equals alpha times A transpose X plus beta times A transpose Y. Well, A transpose X equals B, this B. So what is this? Alpha plus beta B. Is this working or not?
Yes.
Say that again. I can't hear you. Oh, I see. B must be 0, yes. Because otherwise, things will not work. So, since B is 0, so B must be equal to 0 to have 0 in S. For that reason, this will output 0. So it will work. But if B were different from 0, of course, it would not be a subspace in that case. So if it were like that, it wouldn't be a subspace. Okay? Good. I'm sure you must have heard the term span of, yes. So let's pick a bunch of vectors in Rn. The set of vectors y such that y is equal to alpha 1 x1 plus up to alpha k xk for some choice of numbers alpha 1 through alpha k, each in the real line, is called the span of the collection of vectors x1 through xk. So, if you have a bunch of vectors, finitely many, x1 through xk, and if you take any linear combination of these vectors, and if you look at the set of such points obtained as a linear combination, that set is your span. Okay? The span of x1 through xk is a subspace. Why? Why does it contain the origins?
Alpha for 0.
Yeah. Obviously, taking each alpha equal to 0 is a possible choice. So in that case, you obtain origin here for y, and the span contains the origin. That's for sure. And it contains any linear combination of these given vectors, so it's a span. Okay? You can work it out, just making sure that it fulfills the definition of a subspace. Okay? Is the time up? Huh? What time do we have?
30.
Just about. Okay, let's take a 10-minute break and then we continue.